My name is John Basbagill. I'm going to talk to you today a little bit about my research in multidisciplinary design optimization. First, a little bit about me. I'm from Chicago, and I did my PhD at Stanford in civil and environmental engineering. I focused on sustainable design and construction. And just some random facts about me. I've had a number of fun jobs along the way. I worked as a ski instructor in Salt Lake City, and I worked for a company, Rustic Pathways, for several summers, and had a chance to work specifically in rural areas of Southeast Asia. And I've traveled to a number of countries. I'll be going to my 101st and 102nd countries this summer, to Azerbaijan and Georgia. And some of the countries I really enjoyed were Turkey and Swaziland, which is actually called Eswatini now within South Africa. And random fact, yes, I've been in a Bollywood film, although I wasn't really cast. I was in the way in Singapore airport. And so they asked me to be an extra and stand in the background while they filmed. Talking about my research now. This is a picture while I was working for Rustic Pathways in rural Thailand. And while I was in my free time, I kind of wandered around the area and noticed how shoddy here. You can see the insulation of the homes was. Obviously, people are just using local materials, whatever they can find. It was a poorer area. And so in addition to the financial costs, I was interested in the quality of these materials as a way to insulate homes. And so this kind of sparked my interest in building materials and specifically insulation properties of these materials. So I went to architecture school for my master's, and there discovered how much energy buildings consume, upwards of 40%. This is a massive energy demand and a big opportunity, right, for sustainable design. These are some testimonials. I spent a lot of time in the field working with both architects and engineers, and these were for people that I spoke with, not only reiterating this challenge of designing buildings more sustainably, but specifically how we can do that in a more intelligent approach using analytics and AI. These people reiterated the importance of that integration between design and analysis tools. A little background how buildings are done, building designs are done today. So there's this vast design exploration space. You can see here upwards of 10 to the 11th power. This obviously cannot be done manually. It's very intractable, and typically there's only a couple alternatives that are considered by architects. And so this is a very labor-intensive process and not very practical in terms of getting a full understanding of what all the design possibilities are. So this is where AI comes in, and we can leverage our learnings from other industries to design buildings more sustainably. So specifically these industries, aviation, aerospace engineering, and automobile industry, have successfully used AI in what's called multidisciplinary design optimization to consider significant numbers of design alternatives and choose ones that are whatever is of interest: low cost, low energy, low carbon footprint. And so why not use these approaches that have been used in these other industries to the architecture industry? You might recognize, does anyone recognize, actually I'll put it as a question, the building on the right there? If you want to put that in the chat. It's a building you might have seen. You might have been a little young, but back in, I believe, 2008. Yes, it's the Bird's Nest in China for the Olympics, which was sort of one of the first few buildings to use what's called generative architecture, where we're using computers to generate novel designs and do analytics on those novel designs. Okay, so this generated my research question, which is how can automated design exploration support sustainable architectural design? And what I leveraged was multidisciplinary design optimization, which involves the formalization of design iteration and coordination to leverage computer processing power to systematically search the design space. The framework here shows that we start with a geometric model in the industry. It's called a BIM, Building Information Model. And from there, we can feed in those geometric parameters into several design analytics tools. These are going to measure the capital and operational performance of a building in terms of construction costs, operational costs, the impacts of the materials in terms of energy consumption and operational energy consumption. And then the operational impact is the energy and carbon footprint required to power the systems of a building. So that's heating, cooling, water, electrical, etc. So the model considers all of these analytics tools to compute the costs and impacts. And then an optimizer kicks in, which is going to look at all of the design parameters that will help to lower each of those impacts. And this becomes an iterative loop where the optimizer tries out different design parameters and the model updates, and then those metrics are calculated accordingly for each new iteration until the optimizer is happy with the results of achieving whatever the objective is, whether it's minimized cost, minimized environmental impact, or a balance between the two. And then the design iteration stops there. So I'm going to show a video exactly how this approach works using a genetic algorithm.
Dear fellow scholars, this is 2-minute papers with Károly Zsolnai Fehér. Genetic algorithms help us solve problems that are very difficult, if not impossible, to otherwise write programs for. For instance, in this application, we have to build a simple car model to traverse this terrain. Put some number of wheels on it somewhere, add a set of triangles as a chassis, and off you go. This is essentially the DNA of a solution. The farther it goes, the better the car is, and the goal is to design the best car you possibly can. First, the algorithm will try random solutions, and as it has no idea about the concept of a car or gravity, it will create a lot of bad solutions that don't work at all. However, after a point, it will create something that is at least remotely similar to a car, which will immediately perform so much better than the other solutions in the population. A genetic algorithm then creates a new set of solutions, however, now not randomly. It respects a rule that we call survival of the fittest, which means that the best existing solutions are taken and mixed together to breed new solutions that are also expected to do well. Like in evolution in nature, mutations can also happen, which means random changes are also applied to the DNA code of a solution. We know from nature that evolution works extraordinarily well, and the more we run this genetic optimization program, the better the solutions get. It's quite delightful for a programmer to see their own children trying vigorously and succeeding at solving a difficult task. Even more so if the programmer wouldn't be able to solve this problem by himself. Let's run a quick example. We start with a set of solutions. The DNA of a solution is a set of zeros and ones, which can encode some decision about the solution, whether we turn left or right in a maze, or it can also be an integer or any real number. We then compute how good these solutions are according to our taste. In the example with cars, how far these designs can get. Then we take, for instance, the best 3 solutions and combine them together to create a new DNA. Some of the better solutions may remain in the population unchanged. Then, probabilistically, random mutations happen to some of the solutions which help us explore the vast search space better. Rinse and repeat, and there you have it, genetic algorithms. I have also coded up a version of Roger Alsig's Evo-Lisa problem, where the famous Mona Lisa painting is to be reproduced by a computer program with a few tens of triangles. The goal is to paint a version that is as faithful to the original as possible. This would be quite a difficult problem for humans, but apparently a genetic algorithm can deal with this really well. The code is available for everyone to learn, experiment, and play with, and it's super fun. And
all right, so you get a taste of genetic algorithms there. I think what's really cool, a number of things that are cool about genetic algorithms is how multidisciplinary they are. You can see how we're drawing knowledge from art or physics or different aspects of design to optimize something. In the case of the video, it was the design of a car, but in my case, and this really got into the next phase of my research, was the design of buildings. Okay, so this is a case study that I worked on. This was a U.S. Embassy building in Islamabad, Pakistan. And so I worked with the U.S. Department of State and Department of Defense to help them design this building using MDO. You can see here the design parameters here. There were several variables that were under consideration, whether the footprint of this building would have, or this complex would have 3 buildings or 4 buildings, the different orientations, the number of stories, the footprint shape there, looking like an H shape, the window to wall ratio, the percentage of windows on each side of the building, and then several materials and shading parameters as well. Okay, there were only 3 required inputs: the size of the building, the location of the building type, and you can see again at the bottom how big this design space was. So kind of a good use case for MDO. And the results here show that after iterations, a few thousand iterations is what this represents, you can see the performance of the results. So on the y-axis is the cost and the x-axis is the carbon footprint. The closer you are to that lower left corner, the better the design. And you can see the breakdown of the results in terms of building configuration. So 3 or 4 buildings, and then 5, 6, 7, or 8 stories. The blue dots performed the best. So that was the 3 buildings, 5 stories configuration. And the baseline was this plus sign. That was the original design. And so you can see significant improvements both for cost and carbon footprint. And a few examples of designs with the number of buildings, the shape of those buildings, as well as the orientation of the buildings. And also the results show what are called design synergies. So those are connections between the different parameters. What you do, this is called a parallel coordinates plot. You look at the far right and go to your metric of interest. So if we're interested in minimizing carbon footprint, we would gravitate towards the blue lines, and then you can trace back and see all of the design parameters that correspond to high performing buildings in terms of the carbon footprint. And we would notice that, say, for building orientation, it's somewhere around maybe 300 degrees, has a nice cluster of low performing designs there. And then the different shape parameters, the number of floors seems like 5 and 6 perform better than 7 and 8. And 3 and 4, it's kind of split between both, so, in terms of the number of buildings. And I applied this approach on different projects. Here you can see a stadium building, an office building in Atlanta, an educational building, and a residential building as well. So each of these had both significant savings in terms of cost and energy consumption. And lastly, I just wanted to point out, after graduating, I applied my research to a company that I founded. This was a software company that applied MDO to building design to lower energy use and carbon footprint. You can see that I integrated these AI genetic algorithms within the framework of the software that I built. And this is a snapshot here of the actual program that I didn't personally build because I'm not a computer scientist, but I had a team that helped me. And so this is the front end showing the application. And in the background is a picture of SketchUp, which is a building design program. And you can see the integration between the two. So as you make changes with the design, you get a number of updates in terms of the performance of the building, energy, water, cost, carbon, etc. Some sensitivity analysis showing which are the most important design parameters contributing to the metric of interest.